Welcome back, everyone. So, in the prequel to this video, we last left off on identity matrices, where no matter how big the identity matrix is, it is simply a matrix consisting of a diagonal of ones and all the other terms with zeros, as demonstrated right here. And to move on to the present tense for our lesson, we have to cover a few theorems. So, if our coefficient matrix was multiplied by an identity matrix of n, what would that equal? And it turns out it's gonna equal a. The same can be said for if we were to multiply the identity matrix of m by a, which produces the same result, where if a is a matrix of size m by n, then these two properties are true. The same can also be said for if we were to multiply a by the identity matrix such that a is a square matrix of the order n, and as a result we get a. Now let's employ some numerical examples. So we're given a 3x2 matrix multiplied by a square matrix identity. What is the product? You can either type this in calculator or work it by hand, but we know that we're given a 3x2 matrix and a 2x2 matrix. Therefore, we know that the matrix is going to be 3x2. So we multiply each row by each column, and we get 3, -2, 4, 0, -1, and 1. And it turns out that when you multiply your coefficient matrix by an identity matrix, it simply equals a, which is what we have confirmed in this remark above. Now let's do another example. Okay, so we have an identity matrix with n equals 3, so we're gonna have a diagonal with 3 ones in an identity matrix, and we have our coefficient matrix, which ends up being a column vector. So we have an identity matrix that's 3x3, and a column vector is a 3x1, and therefore, what would be the dimension of our product? And if you guessed 3x1, and your guess is correct. Once again, we're going to employ the standard matrix multiplication. We multiply each row by each column, and it turns out the product is just our column vector. Now, for repeated multiplication of square matrices, we will use the same exponential notation used to real numbers. That is, if a to first power is a, and a to second power is a times a, where for a positive integer, so let me write it out. So for a positive integer denoted as k, a sub k will simply be a times a, how many there are, and these simply become our k factors. It's also convenient to note that if our coefficient matrix was raised to the 0th power, it simply becomes our identity matrix, where A is a square matrix of the order n. As a result, these definitions will help us establish two of the following properties. If we have a to the j power times a to the k power, what would that result in? And when two exponents have the same bases, you simply just add the exponents, and as a result, we get a to the power j plus k. For the second property, what if we have a to the j power with the whole term to the k power? And I'll give you guys time to figure that out. And if you said that the exponents can be multiplied to each other, you would be correct. Now, this is only true if j and k are non-integer zeros. Therefore, j and k have to be greater than or equal to 0. So let's say we have a repeated multiplication of a square matrix. Given the matrix where a is equal to 2, 3, negative 1, and 0, what is a to the third power? As we've already established, a to the third power is simply the coefficient matrix multiplied by itself 3 times. And we're going to present it in a way where we have two of the matrices within the parentheses, and then we're going to multiply by the coefficient matrix outside the parentheses. And by following the basic procedures of this equation, we're going to focus on parentheses, and as a result, we are left with 1, 6, negative 2, negative 3, and 2, negative 1, 3, 0, as the other matrix. And let's predict the dimension of a to the third power. Does the dimension deviate from a 2 by 2? And it turns out it doesn't. No, it does not deviate. It's going to be a 2 by 2 matrix. And we get this as the product of a repeated multiplication of a square matrix. Adding on to this example, we'll also dive into the transpose of a matrix. And all that is you're converting the rows within a matrix and you're shifting it into columns. Let me show you guys an example. So here's our matrix A. It's as big as m by n, and let's say that I want to grab this row right here, and I want to transpose A, basically. If I grab each row and turn it to its column, what would that look like? Go ahead and pause the video and figure it out. And while you guys are figuring it out, I'm going to walk through it. By the way, to declare that you're going to transpose a matrix, it's going to be denoted as a to the power of t. And as a result, with each row being converted to a column, we get the first column consisting of A11, A12, A13, all the way down to A1n. And we do the same procedure for the second row, where we get A2n, and then we continue on with the third row, and so forth and so forth. And there you have it. That is how you take the transpose of a matrix. Okay, say we're given A and B, and they happen to both be square matrices. What would the product of AB transpose look like? Well, for starters, we will multiply the two matrices. So that's 1, 2, 3, 4 times the matrix 3, 5, 1, negative 1. Go ahead and pause the video and take the product of that. And let me know what you guys get. So we're going to multiply each row by each column. And we get we get 5. Then we get 5, negative 1. 5 and negative 2, that's 3. And we'll move on to the second row. And then we get 9 and 4, that's 13. Then we have the second row, multiplied by the second column, get 15, negative 4, that is 11. And that is our product. Now, to transpose a matrix is to convert each row into a column. And as a result, the matrix becomes 5, 3, 13, 11. Now, what if we were to have transpose A times the transpose of B? What would that look like? Would you agree that we'd be taking transpose of A and B and then multiplying the two transposes together in that order? And if you said yes, you'd be correct. So let's do that ourselves. So the transpose of A would be 1, 2, 3, 4 times the transpose of B, which is 3, 5 in one column and 1, negative 1 in the second column. And then we multiply and we get a square matrix of 8, and then 1, negative 3, that's negative 2, 6 and 20, 26, 2 and 28, that is 30. And there you have it. That is A transpose times B transpose. My next question for this example is, what if we were to have it as B transpose times A transpose? We only swap the two variables around, so our answer is going to be the same. Well, let's see here. We already got the transpose of B and the transpose of A. Let's see if their products are the same. So we have 8 9 and 4. 9 and 4 is 13. Okay. Moving on to the second row, we get 5 and negative 2. That's 3. Then we get 15, negative 4. 15 and negative 4, that is 11. And it turns out that the commutative property does not apply to matrix operations or to matrix multiplication, even if both terms are transposed. Oh, and by the way, I fixed the multiplication to two matrices, and A transpose times B transpose has 18 in row 1, column 1. I believe that was one of the few mistakes I made doing this. My bad, guys. Okay, in this example, we're given two matrices, A and B. And we have to show that the quantity AB transpose and B transpose plus A transpose are equal. What do? What's the very first thing we do? Well, the first thing we do is often the easiest, and that is multiplying A and B. Let's just find the product of two matrices themselves. And as a result, we get 2, -1, 0, 1, 0, -2, -2, 3, 1, times the matrix 3, 2, 3, 1, -1, 0. Can we predict the dimensions of our product? Well, we have a 3 by 3 times a 3 by 2, and it turns out that the matrix C is going to result in a 3 by 2 product. So we'll multiply each row by each column, and you can pause the video, do it yourself, write through your calculator. I'm going to try to do this as quickly as I can manually. It helps for good practice. We get 2, 6, and -1 in the first column, and 1, -1, 2 in the second column. And there we have the product of A and B. Now, what is the transpose of that product? And once again, every row becomes a column. So we get 2, 1, 6, -1, -1, and 2. Right on. Now, what if we have B transpose times A transpose? For starters, we can take the transpose of the given matrices. So we have 3, 3, 1, 2, -1, 3, 0. And we can take transpose of A, which is 2, 1, -2, 1, 0, 3, 0, -2, 1. So, does this affect the dimensions of our product? And if so, what are the dimensions when both terms are transposed? Well, we have a 2 by 3 times a 3 by 3, and as a result, the dimensions of our product transposed will be a 2 by 3. Once again, you're free to do this yourself when you're running calculations manually. But I got 2, 1 in the first column, 6, -1 in the second column, and 1, -2 in the third column. Now, going back to a question, if I grab this term and this term, do they equal each other? Let's find out. So this is the first term, and this is our second term. It turns out they are both the same matrix, and therefore we have confirmed numerically that these two operations do equal each other.